Okay, so let's talk about the electric grid. We're about to take a journey into this incredible, almost invisible system that, well, powers everything.
So, what is the largest and most complex machine on Earth? I mean, really think about it. It's not some far off spaceship or a massive supercomputer. Nope. The answer is actually all around us, working silently 24/7.
You guessed it, it's the electric power grid. This thing is It's just this vast, interconnected network. It's really the lifeblood of our modern world, right? It brings electricity to our homes, our schools, our businesses, everywhere. And just to give you a sense of the sheer scale we're talking about, in the US alone, the installed capacity is almost 3 kilowatts for every single person. What does that even mean? Well, think of it this way. That's enough juice to run about 30 100-watt light bulbs for each and every one of us all the time.
All right, so how does this invisible giant actually work? Let's do this. We're going to trace the journey of power, step by step, right from the moment it's created to the instant you flip a switch in your house.
Okay, first stop on our journey, the source. We're talking about the generation subsystem where power is literally born inside a power plant.
So, at its core, what's happening here? It's basically about converting mechanical energy, like a spinning turbine that's being pushed by steam or water or wind, into electrical energy. And that whole conversion happens inside a device called a generator. It's really just a giant magnet spinning inside a big coil of wire. Simple concept, incredible results.
And what's spinning those turbines? Well, all sorts of things. The sources are super diverse. You've got your traditional fossil fuels and nuclear fission, of course, but there's also this growing list of renewables. We're talking solar, wind, geothermal, and hey, on the horizon, there's even the promise of clean nuclear fusion. Okay, but here's the thing. We've got our first big problem. The voltage created at the plant, it's just too low for a long trip. If you tried to send it as is, it'd be like trying to use a super leaky hose to water a garden a mile away. It's just crazy inefficient. Most of that precious energy would just get lost as heat. So something's gotta change. A crucial transformation has to happen right here. And that brings us to our next stage, the transmission subsystem. You can think of this as the high voltage highway of the grid, the thing that gets the power ready for its big cross-country journey. So why bother with these crazy high voltages? I mean, we're talking up to 765,000 volts. Well, the answer is simple. It's all about efficiency. These transmission lines are basically the interstate highways for electricity. The goal is to move a ton of traffic, the power, really, really fast, with as little loss as possible. See, by stepping up the voltage way, way up, we can just shove a massive amount of power down those lines. And the best part? We lose very little of it as heat along the way. That's what makes the whole system work. It's way more economical and super efficient. You know this whole high voltage system we have? It exists because of this legendary fight, this war of the currents. On one side, you had Thomas Edison and his direct current, or DC. On the other, George Westinghouse and the brilliant Nikola Tesla with their alternating current, or AC. And AC won. Why? For one simple, game-changing reason. You could easily change its voltage. And that, right there, is what made long-distance transmission a reality. And the key piece of tech, the magical device that made AC the undisputed champion, the transformer. It's an amazing invention, so simple yet so efficient. It can step up the voltage to send it far away and then step it down so we can actually use it, all with barely any energy loss. It's a total game changer. So this is the basic two-step dance that the entire grid is built on. Step 1, you step up the voltage at the power plant for that long-haul trip. Step 2, as it gets close to towns and cities, you step it down for safe delivery to all of us. All right, so the power's traveled maybe hundreds of miles. Now we're at the final stage, the distribution subsystem. This is the last mile, right? How does that electricity actually get to your light switch? Okay, this is where the voltage takes a serious nosedive. That super high voltage power comes off the highway and into a local substation. And there, a whole series of step-down transformers just keep lowering it and lowering it, taking it from as high as 765,000 volts all the way down to the nice, safe 120 or 240 volts that you use in your house. So yeah, these are the local streets of the grid. Those transformers you see on neighborhood poles, they're the final gatekeepers. They're what take the immense raw power of the grid and make it safe enough for us to use every single day.
But hold on, the grid isn't just a static collection of wires and boxes. No way. It's a dynamic, living system that's constantly changing. And like any super complex system, it needs a brain. And that brain is the control center.
So get this. Inside these energy control centers, operators are doing this incredible non-stop balancing act. They're using really sophisticated software to make sure that the amount of power being generated perfectly matches what everyone is using, second by second. If they get it wrong, too much power or too little, the whole system could literally collapse.
I mean, talk about a high-stakes job. Our source material even says that when things go sideways, operators often have to just improvise to keep blackouts from happening. It's this constant battle against the unknown, where one single bad call could have huge consequences.
So, to keep all this from turning into chaos, this whole continent-spanning machine is coordinated by reliability organizations. Think of them as the ones who set the rules of the road for the grid. They make sure that hundreds of different utilities are all playing by the same rules, working together to prevent those catastrophic cascading failures and, keep the lights on for all of us.
So there you have it. We've taken a quick journey through this century-old marvel of engineering, all the way from the power plant right to your home. But what's next? What does the future hold for this incredible system?
Well, the grid is facing some fundamental changes. See, the old grid was basically a one-way street. Power flowed from a few big plants out to everyone else. Simple. But today's grid, it's becoming a complex two-way network. You got energy flowing in from all over the place, rooftop solar panels, wind farms, you name it. And that, as you can imagine, creates some massive new challenges for that delicate balancing act we were just talking about. Which really leaves us with a big, critical question. Our grid was built over a century ago for a different world. So how do we evolve this invisible giant for the next 100 years? How do we build a grid that isn't just reliable, but is also clean, resilient, and truly ready for the future?